Advanced Brain-Computer Interfaces, BCIs, 2025. The journey toward advanced BCIs begins with non-invasive methods that prioritize ease of use and accessibility. Innovations such as wearable EEG, electroencephalography, headsets will enable users to interact with digital devices through brainwave detection. These BCIs will enhance accessibility for individuals with motor disabilities, providing them with new ways to communicate and control their environment. Companies and research institutions will focus on improving the accuracy and reliability of BCIs. Machine learning algorithms will play a crucial role in interpreting complex brain signals, translating them into actionable commands. The collaboration between neuroscientists, engineers, and software developers will drive rapid advancements in this field. As BCIs become more integrated into everyday life, ethical considerations regarding privacy and data security will arise. Ensuring that neural data remains secure and that users have control over their information will be paramount. Regulatory bodies will begin to establish guidelines for the ethical use of BCIs, balancing innovation with individual rights. Neuromodulation for Mental Health, 2028. Neuromodulation techniques, including transcranial direct current stimulation, TDCS, and electroconvulsive therapy, ECT, will undergo refinement to target specific brain regions with precision. These techniques will become tailored treatments for mental health conditions, offering relief for patients who do not respond to traditional therapies. The development of closed-loop systems will revolutionize neuromodulation. These systems will continuously monitor brain activity and adjust stimulation parameters in real time to optimize treatment outcomes. Personalized neuromodulation plans will be created using detailed brain mapping and patient-specific data. Mental health stigma will decrease as neuromodulation becomes a mainstream treatment option. Public awareness campaigns and educational initiatives will emphasize the scientific basis of these therapies, promoting acceptance and understanding. Patients will have access to comprehensive care that integrates neuromodulation with psychotherapy and medication. Brain-to-brain communication, 2030. Early versions of brain-to-brain communication, BTBC, will leverage BCIs to facilitate direct neural connections between individuals. These systems will enable the exchange of thoughts, sensory experiences, and emotions, opening new possibilities for interpersonal communication. Initial applications of BTBC will focus on aiding individuals with communication impairments. For example, patients with conditions such as locked-in syndrome will use BTBC to communicate more effectively. As the technology matures, its use will expand to collaborative tasks, such as team-based problem-solving and creative endeavors. Ethical considerations will be critical in the development of BTBC. Consent and privacy will be paramount, ensuring that individuals have control over their neural communications. Researchers will explore the implications of shared neural experiences on personal identity and autonomy. Memory augmentation, 2035. Memory augmentation will become a reality through the use of neuroprosthetics and neural implants. These devices will enhance memory formation, storage, and retrieval, providing users with the ability to remember vast amounts of information accurately. Neuroprosthetic devices will interface directly with the hippocampus, the brain region responsible for memory processing. These devices will use electrical stimulation to enhance synaptic plasticity, strengthening neural connections and improving memory retention. Users will have the option to selectively enhance specific types of memories, such as factual knowledge or procedural skills. The ethical implications of memory augmentation will be a topic of debate. Concerns about the potential for misuse, such as implanting false memories or erasing unwanted memories, will need to be addressed. Regulations will ensure that memory augmentation is used responsibly and that individuals have control over their cognitive enhancements. Neuroprosthetics integration, 2040. By 2040, neuroprosthetics will achieve seamless integration with the nervous system, providing users with natural control and sensory feedback. Advanced materials and miniaturized electronics will enable the development of prosthetics that closely mimic the function and appearance of natural limbs. Neuroprosthetic limbs will incorporate sensors that detect pressure, temperature, and texture, transmitting this information to the brain to provide realistic sensations. Users will be able to perform complex tasks, such as typing or playing musical instruments, with a high degree of precision and dexterity. The field of neuroprosthetics will expand beyond limb replacement to include artificial organs and sensory enhancements. For example, retinal implants will restore vision to individuals with degenerative eye conditions, while cochlear implants will provide improved auditory experiences for those with hearing loss. Neuroethics Framework 2045. As neurotechnology continues to advance, the establishment of a robust neuroethics framework will be essential. This framework will address the ethical, legal, and social implications of neurotechnology, ensuring that advancements benefit society while protecting individual rights. Key areas of focus will include privacy, consent, and the potential for misuse of neural data. Neuroethics guidelines will ensure that individuals have control over their neural information and that data is used transparently and responsibly. Researchers and developers will adhere to ethical standards that prioritize the well-being and autonomy of users. Public engagement and dialogue will be crucial in shaping the neuroethics framework. Policymakers, ethicists, scientists, and the public will collaborate to develop regulations that reflect societal values and promote the responsible development and use of neurotechnology. Cognitive Enhancement 2050. Cognitive enhancement technologies will offer the ability to improve various aspects of cognitive function, such as memory, attention, and problem-solving abilities. These enhancements will be achieved through a combination of neural implants, neurostimulation, and pharmacological interventions. Neural implants will target specific brain regions to enhance cognitive processes. For example, implants that stimulate the prefrontal cortex will improve executive functions, such as decision-making and planning. Pharmacological interventions will include smart drugs that enhance neurotransmitter function, boosting cognitive performance. The availability of cognitive enhancement technologies will raise ethical and social questions. Debates will arise regarding the fairness of using enhancements in competitive environments, such as academics and professional settings. Regulations will be established to ensure equitable access to enhancements and to prevent their misuse. Neurosecurity Systems 2055. With the increasing integration of neurotechnology into daily life, the need for robust neurosecurity systems will become critical. These systems will protect neural data from hacking, unauthorized access, and other cyber threats. Neurosecurity measures will include encryption protocols that safeguard neural data during transmission and storage. Biometric authentication methods, such as brainwave patterns, will ensure that only authorized users can access neural interfaces. Continuous monitoring and anomaly detection systems will identify and respond to potential security breaches in real time. The development of neurosecurity systems will involve collaboration between cybersecurity experts, neuroscientists, and policymakers. Ensuring the security and privacy of neural data will be essential for maintaining public trust and promoting the widespread adoption of neurotechnology. Emotional Regulation Implants 2060. Emotional regulation implants will provide individuals with the ability to modulate their emotional states through direct neural stimulation. These implants will target brain regions involved in emotion processing, such as the amygdala and prefrontal cortex. Emotional regulation implants will offer personalized treatments for conditions like bipolar disorder, severe anxiety, and chronic stress. Users will have the ability to adjust their emotional responses in real time, promoting mental well-being and resilience. These implants will also enhance emotional intelligence, improving interpersonal relationships and social interactions. The ethical considerations of emotional regulation implants will include concerns about autonomy and the potential for misuse. Regulations will ensure that individuals have control over their emotional states and that implants are used responsibly to promote mental health and well-being. Full Sensory Virtual Reality 2065. Full Sensory Virtual Reality (VR) will provide immersive experiences that engage all five senses. Neural interfaces will directly stimulate sensory pathways in the brain, creating realistic virtual environments that users can see, hear, feel, taste, and smell. Full sensory VR will revolutionize entertainment, education, and communication. Users will be able to explore virtual worlds with a high degree of realism, participate in immersive educational simulations, and communicate with others in lifelike virtual settings. The technology will also have therapeutic applications, such as exposure therapy for phobias and post-traumatic stress disorder, PTSD. The development of full sensory VR will require advancements in neural stimulation techniques and sensory mapping. Ethical considerations will include the potential for addiction and the impact of prolonged VR use on physical and mental health. Regulations will ensure that full sensory VR is used safely and responsibly. Mind uploading trials, 2070. Mind uploading, the transfer of human consciousness into a digital format, will begin experimental trials by 2070. These trials will explore the feasibility and implications of creating digital copies of human minds, potentially offering a form of digital immortality. Mind uploading will involve the detailed mapping and replication of neural connections and brain activity patterns. Early trials will focus on preserving the consciousness and memories of individuals facing terminal illnesses, providing them with a digital existence beyond their physical lifespan. The concept of mind uploading will raise profound ethical, philosophical, and existential questions. Debates will center around the nature of consciousness, personal identity, and the implications of digital immortality. Regulatory frameworks will ensure that mind uploading trials are conducted ethically and that participants provide informed consent. Neuroeducation platforms, 2075. Neuroeducation platforms will transform the way we learn by tailoring educational experiences to individual brain patterns. These platforms will use neuroimaging and neural interfaces to monitor brain activity, providing personalized feedback and optimizing learning outcomes. Neuroeducation platforms will adapt to the unique cognitive profiles of each learner, identifying strengths and areas for improvement. Real-time adjustments will be made to teaching methods and materials, ensuring that learners receive the most effective instruction. These platforms will be used in schools, universities, and professional training programs. The widespread adoption of neuroeducation platforms will require collaboration between educators, neuroscientists, and technology developers. Ethical considerations will include the potential for data privacy concerns and the need to ensure equitable access to advanced educational technologies. Enhanced human senses, 2080. By 2080, neurotechnology will enable the enhancement of human senses beyond natural capabilities. Neural implants and sensory augmentation devices will provide users with improved vision, hearing, and other sensory experiences. Enhanced vision implants will offer capabilities such as infrared and ultraviolet vision, enabling users to see in low light conditions and detect heat signatures. Auditory implants will provide enhanced hearing, allowing users to perceive a wider range of frequencies and improve speech recognition in noisy environments. The enhancement of human senses will have applications in various fields, including healthcare, security, and entertainment. Ethical considerations will include the potential for social inequality and the need to ensure that sensory enhancements are used responsibly and equitably. Neurotherapeutics for aging, 2085. Neurotherapeutics will play a significant role in addressing the cognitive decline associated with aging. By 2085, advanced treatments will be available to maintain and enhance cognitive functions in the elderly, promoting longer, healthier, and more productive lives. Neurotherapeutics will include neural implants that stimulate brain regions involved in memory, attention, and executive function. Pharmacological interventions will target age-related changes in neurotransmitter function, supporting cognitive health. Personalized treatment plans will be developed using detailed brain mapping and genetic data. The availability of neurotherapeutics for aging will raise ethical considerations regarding access and equity. Policies will ensure that these treatments are accessible to all individuals, regardless of socioeconomic status, and that they are used to promote the well-being and dignity of older adults. Brain network analysis, 2090. Advanced neuroimaging and brain network analysis techniques will provide detailed maps of individual brain networks by 2090. These methods will enable precise diagnostics and personalized treatments for neurological and psychiatric conditions. Brain network analysis will involve the use of high-resolution imaging technologies, such as functional magnetic resonance imaging, fMRI, and magnetoencephalography, MEG, to visualize neural connections and activity patterns. Machine learning algorithms will analyze this data to identify biomarkers of specific conditions and guide treatment decisions. The development of brain network analysis techniques will require collaboration between neuroscientists, clinicians, and technology developers. Ethical considerations will include the potential for data privacy concerns and the need to ensure that advanced diagnostics and treatments are accessible to all individuals. Telepathic communication, 2095. Telepathic communication will become a reality by 2095, facilitated by advanced BCIs that enable direct mind-to-mind communication. Individuals will be able to share thoughts and emotions without spoken or written words, transforming personal relationships and social interactions. Telepathic communication will have applications in various fields, including collaborative work, therapy, and education. Teams will be able to share ideas and coordinate efforts more efficiently, while therapists will gain deeper insights into their patients' thoughts and emotions. The development of telepathic communication will raise ethical considerations regarding privacy, consent, and the potential for misuse. Regulatory frameworks will ensure that telepathic communication is used responsibly and that individuals have control over their neural interactions. AI neural integration, 2100. By 2100, artificial intelligence, AI, will be deeply integrated with neural interfaces, creating a symbiotic relationship between AI and human cognition. AI systems will augment human cognitive processes, providing real-time assistance in decision-making, problem-solving, and creativity. AI neural integration will involve the use of neural implants that interface with AI algorithms, enabling seamless interaction between the brain and AI systems. These integrations will enhance cognitive functions such as memory, attention, and learning, allowing individuals to achieve higher levels of productivity and innovation. The integration of AI with neural interfaces will raise ethical considerations regarding autonomy, privacy, and the potential for dependency. Regulations will ensure that AI neural integration is used to enhance human capabilities while preserving individual autonomy and control. Universal neural interfaces, 2105. Universal neural interfaces will be developed by 2105, capable of connecting with any neural device or system. These interfaces will provide seamless interaction between different neurotechnologies, creating a cohesive ecosystem for brain-based applications and services. Universal neural interfaces will standardize communication protocols and data formats, enabling interoperability between various neural devices and systems. This standardization will facilitate the integration of new technologies and promote the widespread adoption of neurotechnology. The development of universal neural interfaces will require collaboration between technology developers, regulatory bodies, and industry stakeholders. Ethical considerations will include the potential for data privacy concerns and the need to ensure that universal interfaces are accessible to all individuals. Global Neurodata Networks, 2110. By 2110, global networks for neurodata will be established, allowing for the sharing and analysis of brain data on an unprecedented scale. These networks will facilitate collaborative research, personalized healthcare, and the advancement of our understanding of the human brain. Global neurodata networks will involve the integration of neuroimaging data, neural recordings, and other brain-related information from diverse populations. Machine learning algorithms will analyze this data to identify patterns and insights that inform the development of new treatments and technologies. The establishment of global neurodata networks will require collaboration between researchers, clinicians, policymakers, and technology developers. Ethical considerations will include data privacy, consent, and the equitable distribution of the benefits of neurodata research. Post-human society, 2125. By 2125, neurotechnology will have fundamentally transformed human society, leading to a new era of post-human evolution. The integration of advanced neurotechnologies will blur the lines between biological and digital existence, enabling individuals to transcend traditional physical and mental limitations. Post-human society will be characterized by the widespread use of neurotechnology for cognitive enhancement, sensory augmentation, and emotional regulation. Individuals will have the ability to customize their cognitive and sensory experiences, achieving new levels of creativity, productivity, and well-being. The transition to a post-human society will raise profound ethical, philosophical, and existential questions. Debates will center around the nature of human identity, the implications of digital immortality, and the potential for social inequality. Regulatory frameworks will ensure that the benefits of neurotechnology are accessible to all individuals and that its use promotes the well-being and dignity of humanity.